Thank you. So, hello everyone. So I'm Haoyuan. You can also call me HY. So I'm going to present Tachyon reliable memory-centric storage system for big data analytics. And this is a joint work with Ali Gozi, Matei, and my co-advisors Scott and Young. So on the left side, that's the AMPLab. I'm a graduate student from there. And on the right side, that's the new Tachyon logo we just got last week. So, okay. So this is the outline of the talk. At the beginning, I'm going to give a very brief overview of the system and what's the problem we're trying to address, and then talk a little bit about research, and then talk about the open source status and the future roadmap. So let's start with the overview. Okay, first of all, memory is the king. So RAM throughput increases exponentially every year. On the other side, disk throughput increases slowly. So then this leads to the consequence that this memory locality is the key to achieve interactive response time. So this has been realized by many, like frameworks already leverage memory to achieve better performance, like Spark, HANA, Cloudera, Impala. So then the question is the problem fully solved? The answer is no, otherwise I wouldn't talk here. So let's use Spark as an example here. We all know Spark here is a fast in-memory data processing framework, and it keeps one single memory copy of data inside the JVM and keeps track of the lineage which derive the data. Upon failure, it will use the lineage information to recompute the data. Say, for example, in this lineage graph, on the left upper side, the map got lost, data got lost, there's a machine failure. So it's simple just to recompute the data to get the data back. So this is how it works. So then, Spark is great. So many companies are using this and significantly increase the performance of the system. So there are still several issues. The first issue is how do you share the data among different jobs? Say you have a very complex data pipeline in your company, and there's one Spark job reads and writes data, and the other Spark job try to read the output of the last Spark job. So this case, on the left side, this one writes to they need to have an external storage to do this. On the left side, in this graph, it writes to the HDFS, and on the right side, it loads from HDFS. So this write process is slow. So this means that the whole pipeline will be slow. So the problem is even more complicated. Say, now you switch to Spark, but you still have some legacy code written in MapReduce, and then you want to put Spark application and MapReduce application in the same cluster. So how do you share the data efficiently and in a good performance between these different frameworks? So previously, it's still like, use HDFS is just slow in this case. So that's the first issue. Then let's talk about second issue. So in many of these kind of frameworks, like Spark, they share the process like between the execution engine and the storage engine. In this case, if you write a program or you have some experimental program, if the execution engine crashes, then the storage engine will also crash. So you will lose all the in-memory data. You will either recompute it or load it from under file system, which could be slow. And then that's the second one. So let's see what's the third issue. So say you have input data and you want to two different Spark jobs to read the input data or some other data. So in a Spark, these different Spark jobs have to load their own copies into their own JVM. So this means that you have a in-memory duplication. And then also, because you have the duplication, also you have the data inside the JVM. So this will trigger a garbage collection issue, especially when you have a very large memory machine like 200 gigabytes memory per machine, or even more, think about several years later. So because of this, this motivate us to do this Tachyon project. We want to enable reliable data sharing at memory speed within and across cluster frameworks as well as jobs. So then we have one slide to talk about the solution. So what's our solution? The idea is simple. So we push the lineage concept, which has been successfully applied at the framework layer into the storage layer. And then, in the meantime, we want to use the memory aggressively. So in this case, we have two facts. The first one is we only have one data copy in memory, no matter it's read or write. But for performance, you may want to have multiple copies for read if you have hotspot. And the other fact is, so the system also relies on the recomputation for tolerance. So this is where Tachyon sits in the stack. So it sits between computation frameworks and existing storage systems like HDFS, S3, GlassDFS. So Tachyon sits in the middle. And then this is the architecture of the system. It has a very simple architecture. It has a single logical master, keeps tracking the location of every file, what's the state of the cluster. And then it has, on every single worker node, it will run a Tachyon worker daemon to manage the local space. And then, besides the worker daemon, we also have a RAM disk to store the real in-memory data. And if your application has a data locality, it will access the RAM disk directly without going through any other process. This will guarantee the memory performance. Also from the graph, you can see that even though we have a single logical master, we have standby masters. And we use Zookeeper to have a master fault tolerance. That's the architecture of the system. So from this architecture, you can see that if the data is in memory, for read, you will have a memory throughput. So what about write? So we have this lineage concept. So the concept is the relationship among files. Say, for example, you have a file A, you have a file set A, which is group file, and your Spark program reads A and generate B, assess another set of files. And then your file set C, you have a Spark job to read C and generate D. So after these two jobs, you have a MapReduce to read B and D to write E, this E. So this whole information about the relationship among these files, how to regenerate this data, is called lineage. So Tachyon keeps this information. And then when an application writes to the system, it only writes a single in-memory copy. And later on, if the data got lost, Tachyon will be able to recompute this lost data. That's the idea behind the system. So then, after this brief introduction, let's revisit all those issues. So now, how to share the data between different frameworks or jobs. So you have this Tachyon in the middle. So you just write into the system at memory speed and also load at memory speed. That's the first issue. And the second one, because we have this Tachyon in the middle, so if your execution engine crashes, your data is still in Tachyon's memory, so it's fine. So it's okay. So for the third one, also you put most of the data in Tachyon. So in this case, two Spark applications, they will be lightweighted, right? So there's very minor data in memory in the JVM. So the GCU issue will be significantly improved. Okay. So after brief overview about the motivation and the problem we are trying to address, let's talk a little bit about research. And I want to point out here is, for the research thing, it's not fully in our open source release yet, but we are working to make it stable and to be in the open source release. So okay, so we said we want to rely on the lineage information to do the recomputation to get the missing data back. But in this case, you have a machine failure. Someone knocked down the machine. So then that server contains some data you computed last month. How do you guarantee the data will come back quickly? So in our research, this lineage concept enabled the asynchronous checkpointing, which means that when the application writes the data into the memory, it's still at the memory speed. And then in the background, Tachyon will be able to asynchronously flash the data into the underlayer file system, which could be HDFS or S3. So then we have an algorithm called edge algorithm to decide the order to do the checkpointing. Say, for example, from a high level, it is we want to check from the lineage graph point of view, we want to check on the leaves first, and in the meantime, we want to check on the hot files with a high priority. And then, based on this algorithm, we can have a theoretical bound on how much cost we need to recompute any missing data to guarantee we have a reasonable SLA on any data. So that's the first issue. For the more detail, you can read our paper offline, and you can also talk with me later. For the second issue is, say we do the recomputation, right? To recompute any data if necessary. So how do you allocate the resource for the recomputation? Say what if you have a high priority job in the cluster and you don't want to slow that job down? So in this case, we worked on our recomputation resource allocation strategies for two common schedulers in the cluster resource manager. The one is priority-based scheduler. The other one is fair sharing-based scheduler. So for the first one, basically we do you have some normal jobs, J1, 2, 3, with different priorities. And then you came up a recomputation job called R2, which recompute some data needed by job 2. So in this case, we launch this recomputation job with the lowest priority, but if J2 requires the data computed by R2, so R2 will inherit the priority from J2. So the story also goes on if J3 also require the same data with a higher priority, so our job's priority will be increased. That's the priority-based scheduler. Then for the fair sharing, we have a similar story, but it's a little bit more complicated showing here. So you have different jobs, 1, 2, 3, they have different shares, W1, 2, 3. And for all the recomputation, they share the same share, which is 1, the minimum share unit in the cluster. So whenever you have any field data, you will put recomputation job for those data under this share. So it guarantees that if there's no other job in the cluster, this will still get a full resource in the cluster, but there are other jobs running with a bigger share, so those jobs will definitely get much more resource from the cluster. So then the problem is sometime later, say J2 also require the data computed by R2. In this case, you see that the partial resource used by J2 will be reallocated to recomputation job R2, and the same story applies to the job J3 also require the same data later, and will share the resource with R2. And after the data has been computed, all the resource will get back to the original jobs. So that's the two scheduler strategies for two schedulers. Okay. So then let's talk a little bit about the performance we've seen. So this is a comparison with the in-memory HDFS. We deploy the HDFS in the in-memory cluster. But it still needs a replication to do the fault tolerance. In this case, for the write throughput, so Tachyon has the memory throughput, right? It can achieve like 450 gigabytes per second for a cluster with 30 nodes. This is EC2 cluster with 10 gigabits Ethernet. So for in-memory HDFS, is quite far behind for the write throughput. And then we did a theoretical computation for the maximum throughput you can get for a replication-based file system. So we assume 2 copies and 10 gigabits Ethernet. So you can see the difference still quite large. That's the green line in the graph. That's the first graph we want to show. The second one is we want to see how much performance gain we can help on the Spark side. So this is one simple Spark job, which is grep. So we run this Spark job in 3 different settings. The first one is we cache the data in the green line. We cache the data in Spark, and in the deserialized mode, and then do the count and do the grep. The second one is it's a green line. We do the Spark cache in the serialized mode, and then we do the grep. And the last one is we just keep the input data in Tachyon. We call it TFS here. So the upper graph is the overall result for a single machine. To examine this carefully, we just use a single machine with 240 gigabytes memory. So as you can see, and on the x-axis, that's the gigabytes, the raw data size in gigabytes from 0 to 180. And the y-axis is the execution time from 0 to 300 seconds for this case. And the bottom graph is the enlarged area of the left side of the upper graph. As you can see that at the beginning, we have a smaller size data, so Spark cache mode is faster than the by loading data from Tachyon. For the deserialized mode, it has no overhead of deserialization. For the Spark cache serialized mode, still it has no overhead of loading the data from outside the process. But when you increase the data size, say for example, when you reach around 40 gigabytes raw data, for the deserialized mode, you couldn't handle more than that. The reason is simple. Because you use the Java object has a much higher overhead memory footprint to keep the data inside the JVM. So you couldn't do more than 40 gigabytes in this case. Then for the Spark cache serialized mode, you can do much more. But still, when you reach 90 gigabytes, you have a serious trouble. One thing is GC issue. The other thing is how to grab the data, how to grab the space from the OS. Let the OS give you the space rather from other process in the operating system. This is also hard. So you can see that from around 80 gigabytes, Tachyon will definitely bring you a lot of benefits here. This is the performance for a single job. So for multiple jobs, you will see better, even better performance. So then after this, we just want to show that for Tachyon, since we provide master fault tolerance, we can recover the master failure quickly. In this case, after realizing the machine is down, the system can recover like within 1 second for several million files in this test. Okay, one more interesting issue we want to talk about here is, Tachyon relies on the recomputation to do this to achieve fault tolerance. So one natural question is how much resource the cluster will be used by the recomputation. So in this, this is a theoretical analysis on the worst case, and we use the trace from Facebook and Bing. And for the cluster size, we use from 1,000 nodes cluster to 5,000 nodes cluster. And on the x-axis, that's the memory size per machine from 128 gigabytes to 1 terabyte per machine. So from the analysis, we got the conclusion that in both traces with 5,000 nodes cluster, the recomputation will not use more than 1.6% of the whole cluster resource. So this is comparing with the average utilization of this cluster, which is around 30%. So 1.6 is pretty small. All right, so then let's talk a little bit about our open source status. So we open sourced under Apache 2.0 license, and we released 0.41 early this year. Just to prove this is true, this is real, we have a snapshot on the GitHub, and we have more than 800 stars here. And then more than 15 companies, they already contribute the code base. And there are several companies that put full-time employee on this. And Spark and MapReduce applications that run on top of this without any code change. So as I said, now you develop new applications in Spark, but your legacy MapReduce code can still run in the same place. So then let's show a little bit more detail about our release growth. Last year, April, we had our 0.2 open source release with 3 contributors. And then we had 15 contributors later last year in 0.3. And in 0.4, we had 30 contributors. And next month, we'll have 0.5 release. And we haven't counted the number of contributors yet, but it should be more. So, okay. The other cool thing is most of these contributors actually come from outside of Berkeley. And we counted it's more than 75% of the contributors, they are from outside. And the other news is from Spark 1.0, so Tachyon is the default off-heap storage solution for Spark. Basically, you can say spark.persist off-heap, then the data will be stored, the RDD will be stored in Tachyon. So we'll have one slide to show how to use it later. And then, thanks to the Red Hat, so Tachyon is also in Fedora distribution. So if your machine is connected to the Fedora channel, you can use one command to install this on your machine. Also, early this year, the company called Agitio Tachyon, they commercially started to support Tachyon commercially. And also, earlier, several days ago, so there is a blog post from Databricks. So H2O did a integration with Spark, and they share the data through Tachyon. And this is a snapshot of the blog post. Okay. The other thing is I want to show is how to use Tachyon. So this is a Spark MapReduce Shark job without Tachyon. So you can see that from Spark, you say file, this is RDD, equals to Spark context, and then load the file from HDFS. This is how you use without Tachyon. And then you have MapReduce and Shark. And then with Tachyon, you simply change the URI from HDFS to Tachyon. As you can see, this should be not hard. Yeah. Thank you. So, and then, as I said, so from Spark 1.0, your application should be able to store the data, your RDD off the heap in Tachyon with a simple API. The first line is what we have shown. You can load the input data is loaded in Tachyon's memory, and Spark just load the data from Tachyon through the RDD interface. And the second line, you will see that this RDD, you can say .persist, and then it's off heap. That will put the data in Tachyon. And this is our initial integration, and we'll make this integration more efficient. And we'll try to try to share the same RDD across different Spark jobs like pretty soon. Also, I want to thanks to our code contributors. There are more than 40 contributors now, and from the following companies like Yahoo, Intel, like Nokia, these companies. And okay, so then let's talk a little bit about the future. The first thing is, what's the goal? What's the goal of the system? So because we got this question a lot. So the goal is pretty simple. So we just want to better assist components in the stack to achieve the better performance or easiness to use. Say on one side, we deeply integrate with a Spark, and MapReduce can also run on top of this. Shark also has a close integration. And as I said, H2O, their framework can also load the data from Tachyon. And also, all these other frameworks, we're also very happy to work with them to have the integration. On the other side, for the deeper storage, for the underlayer storage in Tachyon, we also work with different storage system. Obviously, the first one is HDFS, and we want to support it well. And then we can also support S3, which means that you have an S3 cluster, and you have an AWS cluster, and you have S3 storage. And then by deploying Tachyon, you can easily load your open access data into the Tachyon's memory, and then without access S3 anymore. But you're right, we'll go to S3 later. And then besides S3, you can also work with local file system. You can also work with cluster.fs. This is also a contribution from Red Hat, and also we'll have better support even for NFS and also for Ceph. So of course here, I want to say that we are very welcome any collaboration. So please come to me after the talk if you have interest. And then this is a very, very short-term roadmap. So this is just a short list on a subset of what we are working now. Say, for example, for the Ceph, we want to have the Ceph integration. So this is the effort led by Red Hat, and we want to have the hierarchical local storage. This is led by Intel. So for the hierarchical local storage, it's not to get rid of the local file system, just to manage the local storage better, but you still have the underlayer file system like HDFS S3. And then we want to further improve the Shark performance, and this is an effort by Yahoo. And we want to better support multi-tenancy. This is an effort led by Amplab. So there are many more other things we are building from the lab, and also other many industry collaborators. And of course, if you have some requirements, so please feel free to come to me after the talk. Then this is a summary of the Tachyon. So Tachyon is a high throughput, fault tolerant. It's a memory-centric memory-centric storage system with lineage as a first-class citizen. And it further improved the performance for like frameworks like Spark, And then it has a healthy community with more than 15 companies like contributing within a year. That's all. So if you want more information, you can visit our website and also our GitHub, or just feel free to email me. Thank you. Sure. Thank you. Yeah. What's the question?
So can I use Tachyon to replace the disk I/O from a shuffle operation?
Oh, the question is, can you use Tachyon to eliminate shuffle disk I/O? I believe for now, no, but that's definitely on the roadmap. Yeah, thank you.
Are you planning to, in Tachyon, are you planning to use kind of tiering in memory storage? For instance, strict RAM, lazy RAM, RAM to SSD, while for losers, the drive?
Yeah, so the question is, you have different storage media, and what do you use, and whether you can use it together, right? So for the first question, if you have different storage media, you can just use it now. It's not necessary to be like just normal memory, right? It could be anything. So for the hierarchical local storage, as I said, Intel is working on this feature, and I think will be released pretty soon. Maybe. I'm sorry?
In HDFS3, I've had along with compression, with encryption, on disk encryption.
Encryption.
This, the tiered storage, SSD separation, SSD versus RAM,
Uh-huh.
and disk, the disk chunks, and encryption. That's too big contribution.
Oh, yeah. So basically, in this case, you can have like RAM, SSD, disk. It's okay. Yeah. So
It's not handled by Tachyon. It is not handled by Tachyon.
Oh,
You're not planning.
so if the feature is ready, Tachyon can handle it, but it's not going to replace HDFS or S3. It's just manage the local storage, but not the deep storage like HDFS S3, right,
No,
Yeah.
I'm just trying to say, okay, you're storing blocks in Tachyon memory, yes? You can say these blocks can be moved out from the disk. It's a lazy storage, yeah? These blocks can be moved out from the SSD disk. This block will be lost if it's necessary on the disk drive. You see my point? I'm talking about the Tachyon part, the roadmap on the Tachyon side.
I'm saying when the feature is right, when that feature is ready, what you said can be done in Tachyon, can be handled by Tachyon. That's what I said. But we can talk offline. Thank you. Yeah. Yep.
Way of characterizing the applications that can run on top of asynchronous checkpointing, because not all applications can go through.
That's right. So that feature is not in our. So basically, So basically, we are working on the close integration, but what you said is not there yet. But of course, obviously, it's not everything. So, but most applications which can run on top of MapReduce or Spark should be able to use this. Yeah.
How do you handle files that are too big to fit in memory?
Oh, the question is, how do you handle if the file is too big for memory? So the way is so Tachyon has two ways to do this. One thing is we have a pin operation. Basically, you can pin the data in memory. The other way is we just do LRU. So for the data you cannot fit in memory, they stay in the under file system. And we are working on a generic interface to allow plugging different policies. You can plug in LFU, whatever,
Just like the Spark cache, right?
That's right. Thank you.
So you have some really impressive benchmarks for Tachyon, and I was wondering, are there any reasons why you shouldn't use it? Like, is there a break point where it's small enough that it doesn't make sense, or do you use it for any size?
So the question is when you should not use Tachyon.
Or is there a way?
Okay. So this is a great question. So so I think from the software itself, we are building more features. There are certainly something you couldn't do it now, right? So for example, as I said, we are doing this hierarchical storage. maybe your data couldn't fit in memory at all. So in that case, maybe there's very little benefit in using it. But this will, in order to use it, you need to deploy another layer in your cluster, right? This is the overhead. But along the way, when you build more features, you have more motivation and benefit in deploying it. And also, along the way, since there are several companies that are already using this system, and when this process goes on, when more companies are using this, the product itself, the software itself, will be getting more mature. From that perspective, it's better for you guys to start to do this. But we also welcome anyone to use it right now. Yeah, thank you. Yep.
So, do you actually segment those blocks, create blocks for the client, and then store it in multi-node? And why if one node
So,
crash, how long will it take to recover? The cluster node.
I'm sorry? Oh, so you are saying if it's a single node failure, how long it takes to recover, right? So in the current release, the way you recover, you just load from under a file system. It's just the speed to load from there. And then for the feature, for the research agenda we said, that will take like, from our experiment, it's less than 30 seconds. Yeah, around 30 seconds a minute, that's that level, yeah.
So we are talking about probably lineage coming from different tasks.
Yes, that's right. Yeah.
And that still takes 30.
Yeah, 30 seconds, 1 minute, yeah. 10 seconds, depends on the workload, or how heavy or light your workload is. If your workload is light or bursty, you don't have much data not in memory, not in under file system, but just you did asynchronously, doesn't like affect your performance. But for the recovery, it should be very fast. Yeah.
If you have other questions, we can move them out into the hallway.
Sure. I'll be in the back, so outside the door. So feel free to come to me if you have questions. Thank you. Yeah.